Hello, everyone. I'd like to tell you a little story. On Thursday, May 18, I was tutoring this grade 12 student in integral calculus. The textbook being used is called Calculus, a First Course. We were working in chapter 9.3, question 6. We go through questions 6A, 6B, no problem. I'm able to explain how those two questions work. But then we get to question 6C. And at first, I think I know what I'm doing, but ultimately I could not figure it out. This was somewhat embarrassing since high school level calculus should come easy to me. The next day, I decided to give it another go, and this time I was triumphant. So that's what this video is about, how to solve question 6C of chapter 9.3 in the book Calculus, a First Course. So let's take a look at the question. A raindrop is falling. It has an acceleration function defined piecewise as -9 plus 0.9 t from 0 to 10 seconds, including the endpoints, and also an acceleration of 0 after 10 seconds. We are told the initial values for the velocity and distance of the raindrop. So using all this information provided, question 6C is to figure out how long it takes for the raindrop to hit the ground. But how do we go about this? It would be helpful to find a function that measures the distance of the raindrop from the ground over time. I shall call this function dt. We can then set dt to equal 0 and determine which values of t this equation occurs. But how do we find this distance function? We know that the instantaneous rate of change for dt with respect to t is equal to vt, where vt is the function that measures velocity of the raindrop over time. From now on, when I mean the instantaneous rate of change with respect to t, I will simply call it the derivative. In addition, we know that the derivative of velocity is acceleration. At is the function for acceleration over time, which is provided in the question as a piecewise function. Therefore, the derivative of vt is equal to at.
You can reverse this process of differentiation using integration.
If the derivative of dt equals vt, this implies that dt equals the integral of vt plus some constant. If the derivative of vt equals at, this implies that vt equals the integral of at plus some constant. So to determine an exact equation for dt, we can first find the exact equation of vt through integration, then use this to find the exact equation for dt using integration once more. We will use the initial values for distance and velocity, which are provided in the question, to determine these constants. If you recall, function at is expressed as a piecewise function in the question. Likewise, the integral of at will also be expressed as a piecewise function. From now on, when I am referring to the part of the piecewise function defined when 0 is less than or equal to t is less than or equal to 10, I shall call that piece 1 or the first piece. When I am referring to the part of some piecewise function defined when t is greater than 10, I shall call that piece 2 or the second piece. So let's integrate piece 1 and piece 2 individually for the acceleration function in order to determine the velocity function. For the first piece, a equals -9 plus 0.9 t. Integrate that, you get that the velocity is -9t plus 0.45 t squared plus some constant, which I shall call c1. So that takes care of piece 1 of the piecewise velocity function. For the second piece, the acceleration is a constant 0. The integral of 0 is simply some constant, which I shall call c2.
We have a nearly solved function for velocity. It's not complete since we must determine the values for the constants. Let's start with C1.
If you read the question, it states that a raindrop has an initial downward speed of 10 meters per second. What that means mathematically is that if t equals 0, v equals -10.
But why -10 instead of +10?
Velocity is a vector, which means it has both magnitude, in this case 10 meters per second, and a direction. In this case, the direction is downward. In the context of this question, up is a positive value, while down is a negative value. This is the reason the velocity is negative 10 meters per second. Written in coordinate form, t comma v equals 0 comma negative 10. We already have an equation for the vector function in the first piece. Sub in 0 comma negative 10 into that vector function, and you will find that c1 equals negative 10. But how do we find c2? We know that vt must be a continuous function. Why is that? Imagine a scenario where you are driving a car. You are stopped at a red light. You feel that need for speed, so you decide to slam on the accelerator once the traffic light turns green until you reach a speed of 150 kilometers per hour. To go from 0 to 150 kilometers per hour, you had to have reached every single one of the infinite possible values between 0 to 150 for your speed.
The speed of your car with respect to time is a continuous function. Likewise, acceleration, velocity, and distance are all continuous functions with respect to time.
In fact, the acceleration function provided in the question is continuous. But how does this continuity property help solve C2? Well, consider the definition of a continuous function as defined by its limit. Suppose you have a function, fx. Fx is continuous if and only if the limit of the function as x approaches c is equal to the function value at c for all values of c in the domain. Looking at the function vt, it's clear that each of the individual pieces are continuous by itself. But in order for vt to be continuous as a whole, the function must be continuous where the two pieces meet at t equals 10. This means that v10 equals the limit of vt when t approaches 10. v10 equals 55. But what is the limit of v as t approaches 10? When taking the limit of a function on the real number line, in order for the limit of that function to exist, the left limit must equal the right limit, which in turn equals the limit. So the left limit of vt equals negative 55. The right limit of vt equals c2. Therefore, c2 equals negative 55. So now we have a fully solved equation for vt. What we just solved is called initial value problem, or IVP. An IVP is when you are provided the derivative of some continuously differentiable function along with a single point on the graph of that function, also called your initial value. The task of an IVP is to determine a continuously differentiable function which fits the criteria provided.
So where are we going with all this?
Well, we started with the acceleration function provided in the question, and we know that acceleration is the derivative of velocity. We were also given an initial value for vt. All this information combined forms an IVP for the velocity function, which we then solved through integration. But there's more. We know that velocity is the derivative of distance. We were also given an initial value for dt. More on that later. All this information combined forms an IVP for the distance function, which we can solve through integration, which is what we shall do right now. Going through the same process as before, from 0 to 10 seconds, v equals negative 9t plus 0.45 t squared minus 10. Integrate that, you get that the distance is negative 4.5 t squared plus 0.15 t cubed minus 10t plus some constant, which I shall call k1. So that takes care of the first piece of the piecewise distance function. For the second piece, the velocity is constantly negative 55. The integral of negative 55 is negative 55t plus some constant, which I will call k2. To get the initial value for this IVP, you will notice the question reads, the raindrop is initially 600 meters above the ground. So when t equals 0, d equals positive 600. We know it's positive rather than negative since it reads above the ground. And in the context of this question, up is a positive value, while down is a negative value. Written in coordinate form, t comma d equals 0 comma 600. We already have an equation for the distance function in the first piece. Sub in 0 comma 600 into that distance function, and you will find that k1 equals 600. To find k2, we once again rely on this continuity property for the distance function, just as we relied on the continuity property for the velocity function to find c2, if you recall. As a consequence of d2 being continuous, the left limit must equal the right limit when t approaches 10. The left limit as t approaches 10 comes from the distance equation in the first piece. So therefore the left limit equals d10, which equals 200. The right limit comes from the distance equation in the second piece. The right limit equals the distance equation in the second piece when t equals 10, which simplifies to negative 550 plus k2. Therefore, 200 equals negative 550 plus k2. This is a simple linear equation which can be solved to find k2 equals 750. So we now have a fully solved function for dt. We just need to find for what values of t will get dt equals 0. Since the question is about a raindrop hitting the ground, there should really only be one value of t where this occurs.
But in order to be rigorous, we shall treat the question as if there are potentially any number of values of t for which dt equals 0, and we shall find all of them.
Since dt is a piecewise function, we need to find which values of t, if any, will dt equal 0 in the first piece. Then we need to find which values of t, if any, will dt equal 0 in the second piece. So here is the equation for the first piece. As you see, it's a cubic polynomial. So we are tasked with finding the roots of this cubic polynomial within the range of 0 to 10. How do you go about that?
You might be tempted to fire up your TI calculator and go into graph mode, or open up a new tab in Desmos for graphing. However, no graphing tools are required here. We shall find the roots of this cubic polynomial algebraically.
So I will start by introducing a new function, ft, which equals negative 4.5 t squared minus 10t plus 600. This might seem a bit of an unconventional way to find the roots of the cubic polynomial that we have, but just go with it for now. Now what I'm curious to know is, when is the function ft positive? Well, that can be determined by first finding the roots of this quadratic polynomial ft. How do you do that? Use your handy quadratic formula, which gets you these two exact roots. When you approximate this to 3 significant digits, you get that the roots are negative 12.7 and positive 10.5. So ft equals 0 whenever t equals negative 12.7 and 10.5. But when is ft greater than 0? So I will try my best to explain where the function is greater than 0 visually. And no, your eyes are not fooling you. I really am using Microsoft Paint, but trust me, this will work. So if I want to draw this function visually, first I draw my x-axis. So that's my x-axis. I'll even label it. And if the function has a line above, it's going to be positive. If it's below, it's going to be negative. Okay, so now let's actually draw it. Now, because we know that the leading coefficient, which I'm hovering over now, is negative 4.5, which is a negative number. Because of that, it's going to go up, then it's going to go down. So let's do that. It's going to look something like this. Okay, and we know that this number here, which I will make slightly smaller, is going to be 10.5, this root. And the root on the right is going to be negative 12.7. I'll even put a little label here. Okay, so looking at this graph, where is it positive? Well, it's positive here, this area here, which I will paint in yellow. Okay, so it's positive when t is between negative 12.7 and 10.5. But if the function is positive between negative 12.7 to 10.5, then this implies that if t is between 0 to 10, then ft is greater than 0. Why is this relevant? Well, you will also notice that when t is between 0 to 10, dt is greater or equal to ft, which is greater than 0, as we already established. Therefore, dt is greater than 0. So no values of t in piece 1 will result in dt equaling 0. But is there any value of t where dt equals 0 in the second piece? Well, if dt equals 0, then 0 equals negative 55t plus 750. This is a simple linear equation which can be simplified to get t equals 13 and 7/11ths, or 13.6 when approximated to 3 significant digits. So when you look at the question, how long does it take for the raindrop to fall? The answer is 13.6 seconds.